Okay, so any of you guys had a chance to go over the pre-recorded lectures? So last time we talked about the majority of the material on the multi-distribution. So let me just read what we talked about and then ask you whether you got a chance to take a look. So we discussed the general definition of a multivariate normal distribution, why its density, and then the main property was that any affine transformation of a multivariate normal distribution or a vector with a multivariate normal distribution is again multivariate normal, has a multivariate normal distribution. So affine transformations are transformations that look like this. You multiply by a matrix and you add a constant. If this constant is 0, this is just a linear transformation. So affine transformations are extensions of linear transformations. And the only added information from this lemma is that you will have a normal or multivariate normal distribution. For simplicity, I'll just refer to it as normal distribution. But it's understood that if it's a vector and it has a normal distribution, we mean multivariate normal distribution. So the only added information is that this is the distribution and this is normal, because the mean and the covariance matrix we can already compute using our previous results. Okay, and then marginal distributions of a multivariate normal random vector are again normally distributed. This is a consequence of the previous result. And the conditional distributions are, again, normally distributed. And we talked a little bit about this. And the consequence of this result is that independence and uncorrelatedness are equivalent in multivariate normal distribution, in a multivariate normal distribution. Okay, so I asked you guys to take a look at maybe more on the conditional distributions and the subsequent discussion. So in particular, this slide, maybe this. So any one of you guys get a chance to go over this? So this slide was, did you get the chance? Let's see if there's anything. Chat. Okay, Diana, so do you want to maybe say a few words about this slide? Did you get what the idea was here?
It was just that, like for the multivariate normal distribution, uncorrelatedness implies independence and also vice versa. But you can't say the same about like other distributions.
Oh, great. Yes. Okay. So what can we say in general about other distributions?
That independence implies uncorrelatedness.
Okay, great. Yeah, so independence is stronger. In general, independence implies uncorrelatedness. If two random variables are independent, then they're uncorrelated. But the reverse or the opposite is not in general true. However, in a multivariate normal distribution, this is true. And this is a consequence of this fact. So do you guys remember why this is a consequence of this result? Maybe Diana, do you remember? How did this come about? This result, how do we get this? That uncorrelatedness implies independence in the normal case.
I don't remember, sorry.
Okay, that's fine. Anyone else remembers? So maybe let me ask, what sort of characterizations of independence do you guys know or remember? What does it mean for two random variables to be independent?
The covariance equals 0.
Okay, so the covariance equals 0 is exactly uncorrelatedness. So if you have two random variables, covariance is 0. This means uncorrelatedness, not independent. So it follows from independence, but independence is a different concept. It's like a more or stronger assumption. So how do you describe independence? Okay, pinging in the chat. Okay, so yeah, so one way of so let's say I have so Pini is saying px given y is equal to px. So if you interpret this correctly, yeah, then that was that's one way of so implies independence. So let's say this is the conditional density or the conditional probability mass function. So I form the conditional distribution of x given y, and this conditional distribution does not depend on y. So this is equal to the marginal distribution of x. So as if I did not observe y. And this holds for any, let's say these are the densities. And this holds for any x and y. So it doesn't matter what value of y is, the conditional distribution of x given y does not depend on y. And slightly, so I can say px given y does not depend on y. So this is slightly weaker, but it's equivalent to the previous one. If px given y does not depend on y, then it has to be equal to px. It has to be equal to the marginal distribution of x. We can verify this. And so this is one characterization of independence. There are other characterizations. I go over them either in 2020 lectures or in previous quarter lectures. So this is not how you define independence, but this is one of the manifestations or one of the ways to describe independence. And this is exactly what we're using here. So we compute the conditional distribution of y1 given y2. And this in general depends on y2 through the mean. So this mean depends on y2. You can see it here. And so in general, if this generally depends on y2, then we don't have independence because the conditional distribution of y1 given y2 varies as I change y2. However, if sigma 1, 2 is 0, so we can see that this is not dependent on y2 if and only if the sigma 1, 2 is 0. Sigma 2, 2 in general is assumed to be non-singular, so this can't be 0. We're inverting it. And so if sigma 1, 2 is 0, this is not dependent on y2 anymore. It's just going to be mu1. And this is going to be sigma 1, 1. And this is exactly the marginal. So when this turns out to be mu1 and sigma 1, 1, this is exactly the marginal distribution of y1. And so in that case, we have these are independent. So this equal to 0 implies that this is like this. And so the conditional distribution does not depend on y2, and hence y1 and y2 are independent. So that's the proof. The other way around in general holds, but in this case it's also clear. So if this does not depend, if they're independent, then this means that this is not dependent on y2. It means that this has to be 0. It's easy to try. So does this make sense to people now? Questions about this? So let's see. So suppose I have this normal distribution here. So what would be what sort of independence statements I can make here? So what is independent? Well, first, what is uncorrelated of what? And then if things are uncorrelated, then they're independent. So what can I say is independent of what here? If you understand the previous slide. I guess I have to call on you guys. Maybe I'm gonna call on Phase. Are you there? Can you tell us what is independent here of what? Ethan, maybe? Are you there? Diana? Am I on?
Sorry, could you repeat the question?
So can we make an independence statement here? So what is independent of what? So given that I have this y vector with this distribution, can you like give an independence statement? This sort of vector is independent of that, or this coordinate is independent of that coordinate.
Okay. Is y2 independent of y1?
Okay, great. Y2 is independent of y1. Why?
Because the covariance equals 0.
Right. And because the covariance is equal to 0 and we are in a multivariate normal setting. Otherwise, yeah. This would be. So, okay, good. Any other such statement?
Y3 and y1.
Okay, y3 and y1 as well. Okay, again, because this is 0. Is there anything else here?
I don't think so.
Okay, anyone else? Is there any independent statement? Maybe Pinyi? Are you there? Is there any other statement there? Phase, Ethan? There is one more, which includes actually these two. These two are, in fact, consequences of, I can make a single statement that is stronger than both of these. Can you see it now? So you can say one vector is independent of another vector as well.
Could we just say that y1 is independent to our other vectors?
Of what?
Y1 is independent to the other vectors in the system?
Which is to say
y2 and y3.
Okay, yes, great. So you could say that. So you could say that y1 is independent of this vector, and this is this contains those two information, like the two statements. The reason is that this cross covariance is 0. So this is like sigma 1, 2. So if I set this as 1, this is as 2, in index 1, index 2, then this is sigma 1, 2. And sigma 1, 2 is 0, so this means that this piece is independent of the other piece. And these two statements alone is not enough to guarantee this. So this is saying more. This is saying that, for example, any function of these is independent of any function of this. So for example, from this, I can conclude. So if you go to one of the previous lectures, previous years, one way to describe the independence I explained there, that it's equivalent to any function of one random variable being uncorrelated from any other, or any function of one random variable being independent of the other. So for example, from this, it follows that any function of y1 is independent of any other function of y2 and y3. For example, we can conclude that y1 is independent of y2 plus y3, or y1 is independent of y2 plus, I don't know, 2 y3 plus y2 e to the y3. So this is a complicated function of y2 and y3, but because I have the independence, I have that y1 is independent of any other function of this. So this one follows from this statement, but not from these individually. So this is rather stronger, and we have such a result. So whenever you have a covariance matrix with a block structure, this whole thing is 0 here, then this piece will be independent of the other piece in the Gaussian case. And things may not be consecutive. So you could have like a covariance matrix that is, let's say 1, or say 0, 1, 0, 0, 1, 0. Let's say 2, can be 1. Yeah, it's a little bit difficult, but let's say you could have, like, for example, y1, y3 being independent of y2. And for this, you have to have like the cross covariance. So these two yeah, so these entries would have to be 0. Sorry, not these. Yeah, so these entries would have to be 0 in that case. So if these were 0, then y2 would be independent of y1 and y3, and so on. So the blocks need not be consecutive. Okay. So is this sort of clear, people? Are we good? Questions, comments? So independence, this idea that this block is 0 implies the independence of these two pieces has a lot of information in it. So any function of this piece, this could be a partial vector from the original vector, and this could be another part. These are any function of that I form, and any function of this will be independent of each other. Okay. Questions? Okay, let's move on. So there's this idea of the correlation or whitening that we discussed, and this has some consequence for the multivariate normal case. And I'll let you go over this and over the videos, and let me know if you have questions. So we'll come back and use this property later on, but I'm going to leave it there, and we're going to move on to the next chapter if you have no questions. So the next chapter is just the main topic of this course, which is multiple linear regression. And I'm hoping that some of you guys have gone through the video lectures. Did you get any chance to watch any of the videos on the introduction to this chapter? Okay, yes, Yana. Anyone else? I guess, Yana, we have to ask you again. So what is this about? So can you set up the problem? So did you, have you seen multiple linear regression before?
Just like a tiny bit, not anything like major though.
Okay, but you went through the lecture videos, right? So can you maybe,
Oh yeah.
Can you tell us what is the setup of the multiple linear regression? What did you get out of it?
Pretty much there's like a bunch of variables that you like try to figure out to estimate your dependent variable or y.
Okay, so we have a bunch of independent variables, let's say x1 up to xp, and a dependent variable, and we mostly are trying to model y as a function of x1 up to xp. We're not generally trying to estimate. At some point we might try to predict, but we usually observe both y and x's. What we are trying to estimate is the relation, right? We want to figure out what the relation is between them. And multiple linear regression is a way of imposing that, or assuming something about that relation. Okay, so roughly speaking, let me just mention, what you're assuming is that y is an affine function of x, or if you want, you can think of it as a linear function. So if I think of x as a vector that contains so I'm going to do it maybe here. So suppose you observe covariates that I can collect in a vector, and I put a 1 there as well. So we observe p covariates, so this is going to be a vector, and then I observe an independent response, or sorry, a response variable, which is scalar, and then I want to model the relation. So this could be a general function of x, let's say plus some noise. And this function we are going to model as a linear function in the context of linear regression. So a general linear function of x would be something like beta transpose x. So these are general functions of x. If you remember, a general linear map is like a matrix times x, and the matrix in this case would be 1 by p plus 1, because this is p plus 1. And if you expand this, if beta is like beta 0, beta 1 up to beta p, then this is nothing but saying that y is equal to beta 0 plus beta 1 x1 plus beta p xp plus epsilon. And so we're assuming that we have this expansion. And if you think of the model, if you fix any of the coordinates, let's say if I fix x2 up to xp, and look at this, it's like a simple linear regression. This part is constant. And so in terms of x1, you can see that if I change x1, y is linearly changing with x1. So a general linear function of x1 is beta 1 x1. And so it's linear in each coordinate. But there are multiple of them, and the model is linear in every coordinate. So that's the sort of basic modeling assumption about linear regression. So it's a way of modeling the relation between y and x as a linear function. So if you think of the relation of y to this part, it would be an affine function of this part. But we add a 1 here usually, and it would be a linear function of this whole thing, which effectively, this added 1 here accounts for the intercept, because we always get a 1 in this coordinate. And so it's beta 0 times 1. So this trick allows us to actually work with a linear function of this rather than a affine function of this part. Okay, is this clear? So this is the base. Okay, this is the basic setup, and these have names. So these are called covariates, or this is a vector of covariates, or independent variables, or explanatory random variables, and so on. This is the response, or independent variable, has other names probably. And this piece is the noise. So usually in this course, we're going to assume that the covariate vector, this is deterministic and known. This is deterministic and unknown, and this is random and unknown. This would be random and known. So we get to observe both y and x, but we don't get to observe the beta or epsilon, this added noise. In the usual context of like simple linear regression, if you have seen it, what we have is y is beta 0 plus beta 1, let's say x1 plus epsilon. And if you draw samples from this model, so you get, you draw y1 and x1, draw these, let's say n times independently, you would see that they would lie near or around a line. So this line would be the line beta 0 plus beta 1 x1. So there's going to be a line, and then each one of the points, if there was no noise, they would be perfectly on the line. But because of the noise, they're going to be around this line. Okay, and so in each case, if I take a look at a point here, there is a value which is this guy. This is, sometimes we refer to this as the mean. So I'm going to write it as the mu of x1. This is going to be on this line. So this is x1. This is mu of x1. But then because of this additional noise, this is, let's say, the epsilon. So this jumps around. So sometimes it's here, sometimes this is another realization, for example, then it might be here, epsilon would be negative, and so on. Okay, so you would get things like this. In general, we'll refer to this thing or this as the mean function. And the reason why this is called the mean is because we assume that the expectation of epsilon is 0. So if the expectation of epsilon is 0, we conclude that the expectation of y is what? if I make that assumption, what would be the expectation of y? Beta 0 plus beta 1 x, yeah, or in general, it would be just this mu of x. Okay, so either here or here, it's just going to be this part. This is deterministic, so the expectation of y would be the expectation of this part plus the expectation of this, which is 0. This is bilinearity of expectation. So that's why it's called the mean function, because this is the mean, because this is the mean of the y, mean of the y as a random variable. Okay. If there was no noise, you would observe this mean function. Otherwise, you observe something which fluctuates around the mean function. So this is the mean function. So if you plot the mean function in this case, it would be just this line. So that's the equation of mu of x, mu1 of x, mu of x1. Okay. Questions? So in practice, what we do is that we're gonna work with this setup. So this is sometimes called the population version. This is just a single, represents a single sample. So if I draw a single sample, I just have a scalar and I have one of these vectors and these are random. In practice, you draw multiple, so these are actually not random, but there's just one example of this. In practice, we draw y and x multiple times. So I would draw y1 and y2 up to yn. And then I also have, this is bad notation, but unfortunately I have to do it. So x, I don't know what I called this. Let me see. Yeah, so let's do something like this. So we're going to get, this is going to be beta 0 plus beta 1 x 1 1 up to beta p x 1 p. So I'm using the first index to denote the sample. So a general one here would be yi and then yn. So this would be beta 0 plus beta 1 xi1 plus beta p xip. And then this is going to be beta 0 plus beta 1 xn1 up to beta p xnp. So what we do is for each I, I get to observe these covariate values. So this whole thing is a, if I want to form the vector, it's just going to be so the plus and minus. So we have epsilon 1 plus epsilon 2. This is I, and then so on, plus epsilon n. So what I can do is I can write this as y1, y2, yi, yn. And it's not difficult to see that this can be written as a matrix here. Let me do it like this. It's easier like this. 1 up to 1 here, and then x1 1 x1 2 dot 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 x1 p x2 1 x2 2 x2 p xn1 xn2 xnp, and then beta 0 beta 1 to beta p, and then plus epsilon 1, epsilon 2, epsilon n. So this is called the design matrix. We'll write it as X. This is the beta as we had before. This is now a vector epsilon, and this is now a vector response. Okay. So at the end of the day, my model simplifies to y equal x beta plus epsilon. Okay. So this is n by p plus 1. This is p plus 1 by 1. This is n by 1, and this is n by 1. Okay. So each row is an independent. So each row is an independent draw from model star. Model star is this. Okay, sounds good. So I'm going to look at each one of these columns, and I'm going to call them, this is going to be called the x1. This is column x2. These are now vectors. This is column xp. So each one of them collects the value of one covariate for all the samples. So this is collecting the value of covariate p, pth covariate for all the samples. And so my x would be, so these would be the columns of x, right? And then, okay, so I'm going to call this first one as well x0. So this would be x0. Okay, so if I have this column representation, can I write this in terms of these columns? Do you remember an expansion of x beta in terms of the columns of x? Anyone? Okay, yes, Pini has the right idea. So x beta can be written as beta 0 plus beta 1 x1 plus beta p xp. So when you multiply on this side, you're taking the linear combinations of the columns, or you can write it as just beta j xj, j from 0 to p. And if you compare with this, you'd see that this is just the vector version of this. So if I just think of them as vectors now containing n coordinates, then this is going to be exactly the same as before. So I can write the regression problem as y is equal to summation j from 0 to p xj, beta j xj plus epsilon. So this is the vector form of the problem. And also x0 is the vector of all ones. Sometimes I write it as the vector 1 or vector of all ones. This is just a vector that has ones n times. So I can also write y as beta 0, 1, n plus summation beta j xj. These are the genuine covariates. Okay, so these are all representations of the linear regression model. The most compact one is this, but sometimes these are also useful. Okay. Okay, another question. So x beta, we're going to refer to this as mu. Okay, and this is the mean vector now. And so this belongs to a subspace, a well-known subspace. Anyone knows what is the subspace? The interesting subspace that this belongs to. This vector mu, which is x beta. It belongs to a subspace associated with matrix X. It belongs to a subspace. Anyone remembers? Maybe. Okay. Pini has the right one. Okay. To the image of X, if you remember. So the mean vector, so Yn is in general all over the and if you randomly draw from this model, so we're still modeling these as random. So even if you do drive n sample size n, you could repeat the problem or the experiment another time, get a different sample size n, and so on. So we're dealing with random vectors here. So each time you draw, you get a random vector, and so we treat this as a random vector. And this will be all over the Rn. But the mean part, the mean vector, this part, which is mu, this is going to always rely on the image of X. And so it's more restricted. An image of X usually is a proper subset of Rn. Okay, so and then we're going to make some assumptions. So we already know that the expectation of each one of them is 0, I from 1 to n. And if you remember, the expectation of a random vector is just coordinate-wise the expectation of each one of the coordinates. So this would be 0 as well. So that's one of the assumptions, that this vector has 0 mean. We're going to assume that epsilon i's are independent. And variance of each one is the same and is equal to sigma squared. So same variance for all I, but this sigma squared is unknown. Okay. So if I have this assumption, these set of assumptions, what can I conclude about the covariance matrix of this vector? So if I know that they're independent, all of them, and the variance of each one is sigma squared, what would be the covariance matrix of epsilon? Okay, Pini has the right idea. So it's going to be a diagonal matrix, sigma squared, sigma squared, sigma squared, and 0 elsewhere. So why is that? Maybe Diana, Ethan? Okay, Pini again. EIs are, right, so they're independent. But why the covariance? So what are these off-diagonal elements? So let's say if I have coordinate I, coordinate j here, what is this? So this is going to be the ith entry of this is going to be the covariance of epsilon I and epsilon j. And you're saying that this is 0. So why this covariance is 0? So this is because independence implies uncorrelatedness. So this is true in general. So without any Gaussian assumption, independence implies uncorrelatedness. And the diagonal elements are just sigmas. Okay. Sorry, the diagonal elements are just variances, and the variances are assumed to be sigma. So I can write this as compactly as this is sigma squared times the identity matrix of dimension n. So In is just the matrix that has all the diagonals equal 1, and n here is that saying that this is in n dimension, so n by n. Okay, so we have this. This is the first assumption that we make. Sounds good to people? This is the first assumption. The second assumption, sometimes I refer to this as E1. E2 is a stronger assumption. It includes all the previous one, but we also assume in addition, that epsilon has a multivariate normal distribution. And if this is the case, then we can say that epsilon is just compactly has normal, which means 0, and covariance sigma squared identity. So this is the compact assumption that we can make. This includes all this information. So the mean is 0, that's this. The covariance is sigma squared In, so this, for example, implies this. And because the covariance being 0 also implies independence in the Gaussian case, this is also true. Okay, so this also implies that these are independent. That's from the last property that we discussed. Uncorrelatedness and independence are equivalent in the Gaussian case. So we can, without loss of generality, assume this. Not without loss of generality, but we can assume this, and we have all of these and more. Okay. Sometimes this is helpful. Okay, questions? So there is one last assumption, which is about the x. So let's see, Diana, did you get a chance to get that far? So do you know what the assumption is on x that we make?
I don't think I got that far.
Okay. Anyone else sort of had a chance or looked ahead? Okay, so the assumption that we make about x is an n by p plus 1 matrix. We assume that x has full column rank. So full rank means that the matrix has the maximum possible. And full column rank means that the rank is equal to the number of the columns. And so the number of columns has to be the smaller one. So this is equivalent to saying that so x has full column rank if and only if this is equivalent. So equivalent to n has to be less than or equal to, oh sorry, the number of columns has to be less than or equal to n, and all the columns x are linearly independent. In general, the rank of x is less than or equal to the minimum of the 2 dimensions. It can't be bigger than this. And it's full rank, so x has full rank if rank of x is equal to this minimum, and x has full column rank if rank of x is equal to p plus 1. So this is saying that not only your full rank, but that the p plus 1 is less than n, because sorry, this means this p plus 1 is less than or equal to n. So x has full column rank if rank of x is equal to p plus 1. And actually, we don't need this. Because if the rank is equal to this, then p plus 1 has to be the smaller of the two.
What's the difference between full rank and full column rank?
That's what I'm trying to clarify here. So in general, the rank, so if you look at the matrix, the column rank, there's a column rank, and there's a row rank, and the column rank is equal to the row rank. So there is one rank. This is true in general. So this is equal to the rank. This is called, this number is called this common number is called the rank. So the column rank is the dimension of the column space, and the row rank is the dimension of the row space. In other words, the column rank is the maximum number of linearly independent columns, and the row rank is the maximum number of linearly independent rows. So the maximum, so column rank can be at most the number of columns, because we don't have more than that many columns. So the column rank is at most, let's say p plus 1 in this case. The row rank is at most n, but because they're the same, so you get that the rank of the matrix is at most the minimum of the two. It can't be bigger than this. So a matrix has full column rank if the rank is equal to the maximum that it can be for the columns. And it has full row rank if the rank is equal to the maximum they can be for the rows. So in other words, a matrix has full column rank if the number of columns is less than the number of rows, and the rank is equal to the number of columns. Okay, exactly this. So it has full column rank if the number of columns is less than the number of rows, and the rank is equal to p plus 1. This is easier to remember. Okay. It will have full row rank if n is less than p plus 1 and the rank of x is equal to n. In either case, the rank of x is, so you say the matrix is full rank if this is equality. So if this is true. And depending on which one of the, so the rank is either going to be equal to n in that case or equal to p plus 1. In other words, a full rank matrix has rank equal to either the number of rows or the number of columns. If it's equal to the number of rows, then you have full row rank. If it's equal to the number of columns, it has full column rank. Okay, does that make sense? So in this course, we always assume that n is bigger than p plus 1. So these matrices have more rows than columns. And so if things are full rank in this case, they have to be full column rank. So that's always the case for us. So I can say X is full rank. And because we implicitly assume this, then we're done. So it would have been easier to do it. This is just being very compact. So instead of saying that the number of rows is bigger than the number of columns and X has full rank, I'm saying that X has full column rank. We just imply both of those at the same time. In any case, so that's what we're going to assume about X. Okay. So for example, if I give you this 1 minus 1 0 and then 1 1 0, does this have full column rank? Let's say this versus this. Which one has full column rank? So you're left with two people in the class, Penny and Ethan. So which one has full column rank? Okay, the first one has full column rank. The rank of this is 1, the rank of this is 2, and 2 is the most that it can be in this case. So we have 2 by 2. The rank of these matrices can be at most 2. And the rank of K, X is 2, so this has full rank, also full column rank. This is rank 1, and so not full rank. Okay, that's what we're gonna assume. Okay. So we covered all of this up to this point. So one last piece is from these assumptions. So suppose I have so I have y is equal to x beta plus the noise, right? And assume that E1 is true. So I have expectation of epsilon is 0 and covariance of epsilon is sigma squared in. So from this, I conclude that the covariance of y is what? What is the covariance of y? Ethan, Penny. So the covariance of y would be covariance of mu plus epsilon, and I can drop this mu. It's a constant shift, so that would be sigma squared in. And the mean of y would be the expectation of mu plus epsilon, so this would be mu plus 0. This would be mu. So under these assumptions, the covariance, so the mean and the covariance of y are known. And under the E2 assumption, which is assuming that epsilon is normal, which means 0 and covariance sigma squared in, I can further conclude that y has a multivariate normal distribution, because this is an affine transformation. It's just a constant shift added to epsilon. So y would have normal distribution with mean mu and covariance sigma squared eigen, affine transformation property. Okay, so under this assumption, we know the full distribution under E2 at least. We know the full distribution of y. So still have 10 minutes. So the next step is to try to estimate the unknown quantities. The unknown quantities are beta and the variance of noise. And in order to do that, one thing that we can do is to compute the maximum likelihood. So any one of you guys know what the maximum likelihood is? What is the maximum likelihood estimator? So I'm not sure if I'm on even, but in any case, so the MLE is so the maximum likelihood estimation is the idea that you form the likelihood and you maximize it. And the likelihood for a statistical model, you can describe it as writing down the PDF or the density and viewing it as a function of the parameters. So if I write down, so I have the y, the distribution of y, and this depends on the unknown parameters beta and sigma squared. I write down the PDF. If you go through the formula that we had for the PDF of a multivariate normal distribution, it looks like this. And if I simplify things, I would get a result like this. So that's the so I'll encourage you to go through this calculation. So you'd get and end up with something like that. If y is like this, then the PDF would look like that. Now I view this as a function of beta. I view it as a function of beta and sigma squared. Instead of viewing, if you view it as a function of y, this would be the PDF. If we fix y and view it as a function of the unknown parameters, that would be the likelihood. So statisticians would maximize this function of beta and sigma squared, and the maximizers would be maximum likelihood estimators. Because I have done this in the pre-recorded lectures, I encourage you to go through it. Instead of going through the details, I'll just tell you the result. You can work out the details. If you try to maximize this, you first the strategy is you fix sigma squared, and then try to maximize it over beta, and that would give you instead of maximizing this, it is equivalent to minimizing this quantity. So you first argue that maximizing this over beta is equivalent to minimizing this, which you have to argue for yourself. And then minimizing this is called the least squares criteria. So you're measuring how close your response is to x beta, and you choose beta that minimizes these. This is equivalently the sum of the squares of these deviations, yi minus x beta I. And so in order to do that, this is a quadratic form. You can take the gradient and set it equal to 0. If you do that, again, there is some calculation here, but once you do it, you get this, that let's say the beta hat that minimizes this has to satisfy this set of equations. And these are called normal equations. And At this point, we're not sure whether this is a minimizer or not, but you have to take the second derivative as well and verify that the second derivative, which is the Hessian matrix, that is positive semi-definite. If it's positive semi-definite, then it's a minimum. So I'll go over this in the pre-recorded lectures in some detail. But it turns out that there's only a single solution. So let's say assume that the solution of this is the minimizer, then we can generally solve this if we know that this is invertible. So if we know that x transpose x is invertible, I can multiply by the inverse on both sides and I get this formula for beta. So there's a unique solution. And this is going to be invertible when x has full rank. So you can verify that if x has full column rank, then x transpose x is also full rank. And this is a square matrix. This is like P by P. And being full rank means it's invertible, full rank, which is equivalent to being invertible for a square matrix. Okay. And so this is invertible. I can multiply by x transpose x inverse on both sides, and this would be identity, and I get this result. So I get this formula. So that would be the maximum likelihood estimator of beta hat. And from this argument that we did here, it follows that the maximum likelihood estimator for beta is in fact the least squares estimate. So it minimizes the least squares criteria. So you have to go through this argument to convince yourself that maximizing this is equivalent to minimizing this. But the end result is that the maximum likelihood estimator of beta under a Gaussian assumption is the same as the least squares estimate. And the least squares estimate, this estimate in general makes sense, even if you don't assume the Gaussian distribution assumption. So that's the estimate of beta. And in order to estimate, so there is a geometric interpretation, which is very important. I'll come back to this next time, and I'll ask you guys to go over this from the pre-recorded lectures. But let's move on to estimating sigma squared. So once I, so this was S beta here. So, so if you call this, remember, if you call this S beta, this part is S beta. So once I estimate beta hat, I can put beta hat here and then try to optimize over sigma squared. So that's what we are going to do. We're gonna look at this partial likelihood now. So I plug in beta hat, the MLE for beta, and then I try to maximize over sigma squared. And this is a univariate problem. Doing some sort of calculation, taking the derivative, it turns out that the sigma hat is the estimate that maximizes this is S beta hat divided by n. So S beta hat is just y minus x beta hat. And this thing is called mu hat. So x beta hat is called mu hat, the vector of fitted values, and E, the residual is called y minus x beta hat. And so this is just E squared. Okay, the residual vector is squared. So the sigma hat, the squared is just E squared divided by n. And this is just the the residual sum of squares divided by n. That's the MLE for sigma hat. We'll come back to these residuals, but that's what the we'll see what the meaning of these fitted values and the residuals are geometrically. But that's the estimate. In practice, what we do is that instead of working with this MLE, we work with a modified version. So this, instead of that, the MLE, we're going to use this estimator. And the reason is that this estimator turns out to be unbiased. So sigma hat is not unbiased for sigma, whereas sigma's s squared is unbiased. Unbiased here means that the expectation of s squared is equal to sigma, whereas the expectation of sigma hat squared is not equal to sigma in general. So this we'll see later, but that's the common estimator. So so we now know how to estimate sigma squared and s squared. For the next time, I ask you guys to take a look at this geometric interpretation at least, and the details that we went over. And this geometric interpretation is very important for us, and we'll spend some time discussing this. Okay.